Hello, this video will be covering our walkthrough for Lab 11, Test of Means. So this is our first numeric data test. We're going to test whether the mean corresponds to something we think it is. So in this lab, we'll first cover the t-distribution. How does the t-distribution work? This is something we'll be using to find our t-confidence interval, and that'll be all I cover in this video. Next video, we'll cover the t-test with p-values. So what is the t-distribution? It's very similar to our normal distribution. However, its tails are thicker, meaning more of the data falls outside of the mean. So here's the t-distribution with 1 degree of freedom. And notice the tails go farther out. There's more area underneath them. Okay, so that's the t-distribution with 1 degree of freedom. And let's do this for 2, 4, 6, and 8. So here's the t-distribution with 2 degrees of freedom. And I'm going to copy this 4 times. 1, 2, 3, 4, or 3 times. And we're going to go 4, 6, here for the degrees of freedom, and 8. And I'm going to change the colors. Maybe we'll do orange, red, do rainbow, purple, and then blue. So I can notice the difference. And one more thing I'm going to add for each curve I make, I'm going to say add equals true. And this is an argument that allows me to plot lines on top of each other. Okay, so we put comma add equals true inside the parentheses. So careful check on the parentheses. If that runs right, we can see the differences between blue, purple, red, and I'm going to change my y-axis on this one, y-lim. Looks like I need to go from 0 to 0.4. So I say C to denote an interval, 0.4. Now let's run that again. Okay. Yeah, I just wanted to be able to see the top of my curve. So you can see as the degrees of freedom gets higher toward blue, it gets more and more higher peak, but narrower distribution. So interesting note is that as this t-distribution gets bigger and bigger degrees of freedom, it gets closer and closer to the normal distribution. But here's how we find areas of the t-distribution. Suppose we want to find that lower tail probability. Well, instead of p-norm, we'll use PT, physical therapy. And if we're looking at the cutoff value of Q is -2, we'll say PT Q -2, and then we just put in the degrees of freedom, whatever degrees of freedom we're looking at. So here's the same graph with upper tail of 2. So to find that area, how do we do that? We'll do PT, and then instead of Q is -2, we're looking at 2. Degrees of freedom is, I think we're at 18 again. 18 degrees of freedom. And this will give me my lower tail. So to get the upper, I can say 1 minus. That's one way to do it. Or I could say, if I like to say, notice these arguments pop up. Tip. Pops up. So Q is equal to 2. Degrees of freedom was 18. There's this lower tail argument. You could say false to mean upper tail. And that's another way to do the same calculation. All right, forgot my equal sign there. Okay, so that's the key distribution. Here's a few more examples for you to work on, and then you can check your work. Please do these on your own. We're looking at the upper tail of 1.65, 20 degrees of freedom. Check your work on that one. That was the upper tail. What about we're looking at above 1.65 or below -1.65? So if I plot this, but also flip it, That's interesting. Since it's symmetrical about the mean, notice the center of our t-distribution is 0. We'll just double that. So if we double that value, we get the probability of being above 1.65 or below negative 1.65. I'll let you work on number 5. And then now we're going to talk about our confidence intervals. Okay. So here's the picture. We got our population, and we sample from the population, and we get X bar, which is a mean of some kind of numerical variable. Sample mean. And then we're also going to get something called the standard deviation of our data. I'm just going to call that S here. S is the sample standard deviation. And those are being used to estimate mu, some kind of population mean. And often we don't know sigma. Often it's unknown. That's our population standard deviation. Okay, so we're going to use inference. We're going to take the theory of many, many samples. If we sample many, many of these things, what's the distribution of all the means? X bar 1, X bar 2, X bar 3. That will follow a specific distribution for which our sample is one of those points. Okay, so to be able to do this test, we need 2 conditions to be satisfied. We need to be independent. Oh yeah, here, the standard deviation of our sampling distribution in this case will be sigma over square root of n. Sigma is our population standard deviation. At this point, we should notice a problem. We often do not know that. We don't know what the population standard deviation of any size sample. So what we do is we say, hey, if we have a large enough sample, we can use some assumptions. So first we want to assume independence, and we have to have a large enough sample size. Usually this means our n is greater than 30. Our n is greater than or equal to 30, then we're usually good enough. It's less than 30, we'll check. Are there any clear outliers? So with that, we can make an assumption that our population standard deviation is the same as our sample. And then we'll use this formula here for our standard error. Okay. So this step here is very iffy. If we're going to make this step, we got to consider there's some more room for error. And so this is where the t-distribution comes in. It's got those fatter tails to account for less certainty in our data. Although as n gets bigger, it becomes more and more accurate. So the t-test, these differences are especially apparent when we have small samples. So let's look at a small example. So whitefish. We're looking at fish in the ocean, and we only have 15 samples. We're measuring mercury content. We want to know what's the mercury content of my fish? How safe is it? So if we computed the mean and standard deviation were 2.78 parts per million mercury, that was my mean. Or we say X bar for X, the line on top. Standard deviation was 0.069, and we had only 15 fish. Okay, that's our data. So based on this, we don't have a very big sample. That's not a problem if we can still check. Since it's less than 30, can we assume there's no clear outliers? So how do we identify clear outliers? Clear outliers, we can see from a normal distribution, if we look at our data and assume it's a normal distribution, we got 0.287, and we want to be within 2 standard deviations to the left and 2 standard deviations to the right. If our data is within those range, we can be pretty safe. Let's see if we can find that. If X 0.287 is our mean, let's go 2 standard deviations to the right. Here was our standard deviations. So if we look at that, 2 standard deviations to the right is 0.425. Okay. And let's do the same thing, but go 2 standard deviations to the left. 0.149. Okay, so this covers about 95% of my data. So anything outside of that, potential outlier. But if our data lies within that range, there's no clear outliers. So let's look at what our range is. Our lowest data point was 0.18. That's pretty safe. That's within our potential range. Our biggest value was 0.41. That's also within our potential range. So our data is not too skewed. There's not too much potential for outliers, given that it fits within our 95% range. So we'll use that to say all our data falls within 2 standard deviations. So no clear outliers. Then we're safe to assume normal conditions. So that's how we check our assumption if it's less than 30 here. So we've done that. We've checked our assumptions. Now we can proceed to find our confidence interval. So here's our new formula for a confidence interval. We got X bar, which is the sample mean. Standard error is this standard deviation of our sampling distribution. We're assuming we're sampling from this kind of thing. So we find the standard error is S over the square root of N in this case, in this test, different standard error. And T star says, hey, how do I make sure I'm under a certain percentage of data here on my T distribution with a certain degrees of freedom? So to find this value for T star, we first want to know what is our significance, or what is our confidence. So suppose we want a 95% confidence. That means we're looking at 5% significance, 0.05. And so we want to say, hey, I got 95% of the data in here. What value for T do I need to use for left and right to cover 95% of my data? So for that, instead of PT, we're going to use QT. So if we look at our significance, that's alpha, at 0.05. We need to make sure we know what N is. And then we say QT, whatever our significance is, and we divide it in half to make 0.05 divided by 2, 0.05 divided by 2. That means our whole tails add up. And we're going to say QT of our degrees of freedom, N minus 1. So that's our minimum value. That's how far we have to go to the left. And if we want to find the upper tail, well, it's going to be the same value, but it's going to be 1 minus that. So run that. This tells us we have to go 2.14 to the left and 2.1 for the right. So now we're set up. We're set up to do everything. I think I copied these values here. So to find our 95% confidence interval, First, we got to find out what our standard error is. So that's all good. And once we have that, we just use our formula. X bar plus or minus the t value we found, which is that. That's how far we have to go to the left and the right to get 95% of the data. There's our 95% confidence interval. So this is 95% of the fish we have will have this amount of mercury. So between 0.24 and 0.325 parts per million mercury. So now we can say, is whitefish safe to eat? If the FDA says, hey, you can have 0.46 micrograms per gram parts per million mercury, is it safe? So safe would be 0.46 or less. If you draw it on a number line. And we found anything from 0.24 to 0.325 is what you'd expect for my whitefish. So it looks like whitefish is in the safe zone. Yes, it's safe to eat. So now your job is going to be to do the same test. We're going to do the same confidence interval for dolphins, and we're going to see if dolphins are safe to eat. See if you can replicate this process. And I think the trickiest part is here when you get to finding QT. I'll give this to you. By 2, and don't forget your degrees of freedom is your sample size minus 1. We had 19 dolphins. So when you find your confidence interval, you're going to go X bar minus that distance to the left and plus that distance to the right. You still got to recalculate these values here as we did in the previous problem. So then tell me once you finish that, are dolphins safe to eat? Okay, we'll continue in the next video doing a test, the same test, but using the p-value hypothesis test. Okay, good luck.